Welcome student. Nomenclature of fused heterocyclic ring. In the previous lecture of heterocyclic nomenclature, we have discussed travel name replacement system and IUPAC Hans-Widman system as well. And in that one, Hans-Widman IUPAC nomenclature, we need to discuss the fused heterocycles. So this is the second part of the nomenclature. Along with this part, today we are going to discuss regarding a 5-membered 1,3-azoles. That means 2 hetero element containing heterocyclic compound. And then today we are going to discuss regarding the fused heterocyclic compound as well. I am Dr. Devangar Pandya from the Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Well, the numbers here indicate in the heterocyclic compound which atoms in the minor ring are common to the major ring, that is fused site in the minor ring, and the order of the numbers indicates which atom of the minor ring is encountered closest to atom 1 in the major numbering system. These numbers may be written in ascending or descending order like 2, 3 or 3, 2, etc. The latter defines the position of attachment of the minor ring to the major ring, that is a fused site in the base component. Finally, a suffix indicates the name of the base ring is written. The numbering system for the whole fused system is not the same as the numbers in the square bracket. There are 3 numbering systems, one for minor ring, one for major ring, and third is for system as a whole. The priority order of the component ring systems. Selection of a parent component or attached component is based on the rules which are applied in order. Here there is rule number 1. A heterocyclic ring containing the heteroatom occurring earliest in the order, that is nitrogen, fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, etc. Ring containing nitrogen preferred to the rings does not contain nitrogen or containing oxygen or sulfur. That you need to note down. Here you can see the priority should be given to the ring which has nitrogen, and that is why numbering is given from the nitrogen. You can see here 1, then 2, 3, 4, 5, and here this green line indicates that is this base ring fused with this ring contain oxygen. So here the numbering should be given from the heteroatom oxygen. 1, 2, 3. So here 2, 3 is going to be the common wall, and here 3, 4 is going to be the common wall, and nitrogen to first carbon, that is called wall A, this is wall B, and this is common wall C. So if we want to give the nomenclature to this compound, it is chromeno 2, 3, that is 2, 3. This 2, 3 is for this ring system. 2, 3, and for this ring system it is C. So C is mentioned here, and this ring is known as pyrrole. So chromeno 2, 3C pyrrole. That is the nomenclature of this compound. Well, here is the another example when oxygen sulfur is there. Oxygen is the element which given priority. So this is going to be a base ring, and 1, 2, 3 and so on. Oxygen to carbon, this is wall A, this is wall B, and this is going to be the common wall. Here the sulfur is the element for which we can give numbering like 1, 2, 3, 4. So 2, 3 is going to be the common wall. Parenting ring, that is a base ring, oxygen preferred to sulfur is furan ring. Thiopyrano with one started carbon that take locant 7 you can see over here, when the system is numbered as a whole, this is system numbered as a whole, 1 2 3 4 5 6 and 7. System is numbered as a whole. Starting from oxygen, give the two heteroatoms locants 1 and 4. So here you can see this is 1 and this is going to be 4, while starting from S gives them locant 1 and 5. We will starting from here 1 2 3 4 and this is going to be 5. But as far as our nomenclature system is concerned, we need to consider the parent ring, we need to consider the fused ring, and then some unsaturation if there, we need to show that unsaturation as well. So you can see on carbon number 7, unsaturation is there, so 7H. Thiopyrano, that is this ring, and this ring has 3,2, that is the common. 3,2 is going to be the common wall, and then B is the common wall, so 3,2B, and that is furan. So furan is written over here, and that is the way you can give nomenclature to this compound. Rule 2. A heterocyclic component containing the largest possible individual ring, here you can see this is going to be a base ring, this is going to be your another ring, and here you can see this one indicates the proton over here. So first number is this one, first, second, third, fourth and 5, you can say in that way. And as far as this one is concerned, 1 2 3, this is going to be a wall, common wall of oxygen to carbon, that is A wall, and this is going to be a B wall. Now the name of this compound can be written as 2H furo 3,2B pyrene. Pyrene 6 preferred to furan because both the oxygen containing heterocyclic rings are there, and that is why 6 member is given more priority. So this is going to be a parent ring, this is going to be a fused ring. Now numbering the whole system is started from oxygen in furan, furan ring to give the two heteroatoms locant 1 4, while starting from oxygen in pyrene ring gives them locant 1 5. Thus the indicated H takes locant 2. Rule 3. A heterocyclic component containing the greater number of heteroatoms of any kind. Here you can see that nitrogen containing ring, both are nitrogen containing ring, but here oxygen is there. So this is going to be your base ring, and this one 5 numbered is having a proton, hydrogen, so 5H. Pyrido 2 3, 2 3 is the common wall, and D is the common wall, so 2 3D, that is written into box bracket. 1 2 oxygen preferred to pyridine. So oxygen is preferred to pyridine because already 6 membered ring, nitrogen containing ring, but here one more hetero element is there, so this is going to be a parent ring. Now note that the whole molecule is numbered starting from pyridine ring to give the 3 heteroatoms to the lowest locant 1 6 7. However, starting from oxygen ring will give them locant 2 3 5 or 2 3 8. Rule number 4. A heterocyclic component containing the greater variety of heteroatoms. So this is the structure where here you can see here 2 nitrogen is there and 2 nitrogen and oxygen is there, both is 5 membered ring. You can see here this one is having a proton, so that is locant 1. This is overall numbering is given over here, but we need to go for individual numbering as well according to the rule. So 1H pyrazolo 4 3, this is 4 3. D oxazole, oxygen and nitrogen preferred to only nitrogen. So here 2 nitrogens are there and oxygen nitrogen is there, so this ring is going to be a parent ring and this one is a fused ring. The whole molecule is numbered starting from pyrazole ring to give the four heteroatoms the lowest locant 1, 2, 1, 2, 3, 4, 5, 6. So that way 1, 2, 4, 6. While starting from oxazole ring, give them locant 1, 3, 4, 5 or 1, 3, 5, 6. Rule number 5. A heterocyclic component containing the greater number of heteroatoms most preferred when considered in order: fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, antimony, bismuth, silicon, germanium, stannous, lead, boron and mercury. So this is also five membered rings, but here oxygen is going to given a priority. So nitrogen oxygen containing ring is going to be a parent ring. This is going to be a fuse ring. Overall numbering should be given from this, so that the lowest number should be given to the hetero elements. 1 3 thiazolo, 5 D, 5 for D, 1 3 1 3 oxazolo, 1 3 oxazole. Rule 6. A heterocyclic component with the lower locants for heteroatoms. Here you can see that these two are there, but here these two nitrogens are closer, so this one is given priority compared to this one. Pyrazino 2 3, that is 2 3 D, pyridazine. Now this is for your exercise. You need to give this nomenclature to this compound. You can see this priority should be given to this ring rather than this one. So that way you need to give this nomenclature system yourself. This is for your self-study. Rule number 7. If a position of a fusion is occupied by a heteroatom, the name of the component rings to be used or so chosen as both to contain the heteroatom. Here you can see both ring, and this one is going to be on the common wall. So this one is given priority to this. So priority should be given to this one, but overall numbering should be given in such a way that this two nitrogen will come in closer to each other. So it is imidazo 2 1 B wall is the common, thiazole. Order of preference between alternative numbering system of a whole molecule. Numbering the whole fused system should start from the first atom after fusion in any direction to fulfill the following rules in order. Give low numbers for the heteroatoms as a set. Here you can see three example has been given, and a lower number should be given in such way that this one is going to given as 1 hydrogen. So this is the proper numbering. 1H furo 2 3. Here 2 3 is going to be the common wall if this considered as 1 2 3. So 2 3 D is the common wall. Imidazole. Heteroatoms 1 3 4 is preferred to 1 3 6 or 1 4 6. Give lower numbers for heteroatoms for higher priority: oxygen to sulfur to nitrogen. So here the priority has been given. Oxygen is given more priority compared to sulfur. So it is 4 5 dihydrothiono 2 3 B furan is the nomenclature of this compound. Give lower numbers to the fusion carbon atoms. Here you can see three example is given. This is not, this is not. This way we can give the number. Imidazo 1 2 1 2 4 triazine fusion carbon, that is 4A is preferred to 8A. So if we are going to give numbering from this side, it is going to be your 8A. But if we give numbering from this side, it is going to be a 4A. So 4A is preferred compared to this 8A. So these two are not considered. This one is considered for the proper nomenclature. Give lower numbers to indicate hydrogen atom. Lower number for hydrogen atom, here you can see this one is there, so here this one is getting lower number, this one is getting higher number, so this is considered not this one, and therefore here this is the hydrogen and this one is the hydrogen, so 2 4 would be a lower number compared to this 2 6, so this structure should not be considered, this numbering should not be considered, this numbering is right. 2H 4H 1 3 dioxol 4,5-D imidazole indicated hydrogens 2,4 is preferred, not 2,6. This is for your practice. Do it yourself, the nomenclature of this compound. Now, scheme for deriving the base component of a fused ring system, or we can say summary of the nomenclature rules. Is there only one ring which contains nitrogen? That you need to find out. If yes, choose this as a base component. Are the two rings have the same heteroatoms but their size is different? If yes, choose the larger one. Are there two rings of the same size but have different heteroatoms? Then choose the ring containing a heteroatom of a highest priority, oxygen to sulfur to nitrogen, that way. Are the ring of the same size but contain different numbering of the heteroatoms? Then yes, choose the ring with the greater number. Are the two rings of the same size and the same number of different heteroatoms? Then yes, choose the ring with the greatest variety of heteroatoms. Are the two rings have the same size and same number and type of heteroatoms? Then yes, choose the ring with the lower numbers for heteroatoms. So these are certain rules that you need to keep into mind for giving nomenclature to the compound. Now next we are going to study the 5-membered and benzo-fused 5-membered heterocycles, and for that we have oxazole, isoxazole, thiazole, pyrazole, imidazole, benzimidazole, and benzthiazole. Here we are going to include the study of imidazole and benzimidazole after studying the common for these 1,3 azoles. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Well, why to study this compound? What is the importance? Because see, importance will going to gives us temptation, and temptation will put compulsion, and compulsion make us work. So the general chemical behavior of aromatic heterocyclic compounds will make us study these things. General chemical behavior, as I've said, the behavior is such that it gives antibacterial, antifungal, anti-cancer activity. So biologically it is important, and it will also give some better dyes as well. So industrially it is applicable as well. The synthesis is useful to study, so we're going to include that one as well. Important applications are there. What kind of applications? Biological application is there, industrial application is there, and we're going to include the 3 example for each application. So this much is the things that we need to study for this 1,3 azoles. 1,3 azoles, and in that 1,3 azoles our main studies today is imidazole and benzimidazole, then thiazole, benzthiazole, oxazole, benzoxazole, isoxazole we'll going to learn later. Let's start with the introduction. The replacement of a methylene group, that is CH2, in 1,3-cyclopentadiene by nitrogen, oxygen, sulfur result in the formation of pyrrole, furan, and thiophene. 5-membered heterocyclic compounds with an additional heteroatom are termed as azoles. The azole containing 2 nitrogen atoms, 1 oxygen and 1 nitrogen atom, 1 sulfur and 1 nitrogen atom in the 1,2 position are known as 1,2 diazole. They are 1,2 position, 1,2 position oxygen, nitrogen, 1,2 position sulfur. These are 1,3 position, and these are the example of 1,2, and that compounds are pyrazole, isoxazole, isothiazole. These are the 3 compound which have 1,2 position of 2 heteroatom in a 5-membered ring. And when both the heteroatoms are present in 1,3 relation, they are referred to as imidazole. This is imidazole 1,3 position, and 1,2 position is pyrazole, imidazole. Isoxazole, that is 1,2 position, 1,3 position is known as oxazole. Isothiazole is 1,2 position, thiazole is 1,3 position. So that way we can remember this compound by their trivial name. Many azole comprising the ring system of several natural and synthetic compounds which are important for living systems and also as important for drugs, dyes and agriculture chemicals. Already I have said that these are the compounds which are having biological applications, especially in the human health living system, as in the drug industry, dye industry, agriculture chemicals, pesticides, etc. So they have wide range of application which make us tempted to study this compound, and that temptation make compulsion, and that compulsion makes work. Now property. 1,3 azoles, these are going to be the common property for 1,3 azoles. That means 1,3 position 2 hetero elements are there. 1,3 azoles are basic in nature as they have 2 electron available for donation. All azoles are aromatic as the lone pair of electrons on the heteroatoms contributes towards the aromatic sectet. For the construction of molecular orbital structure, each carbon atom contributes one pz electron. The nitrogen atoms gives the fourth electron, and the second hetero element gives two electrons to complete the aromatic sectet, and that is how it's going to be an aromatic compound. So here you see the structure of aromatic compound. Each carbon is having pz electrons, so 4 are there and 2 from the hetero element, and total sectet is going to be generated into the ring. From the diagram it is obvious that the azole nitrogen possesses an electron pair which is situated in the orthogonal fashion to the molecular pi cloud. In this pair of electron which permits the azole to behave as basic compound and as nucleophile as well. So these two electrons are responsible for the basic nature as well as the nucleophilicity of these compounds, 1,3 azoles. Now the various structure of 1,3 azoles, you can see resonating form we will going to obtain when you can see this electrocloud shifted over here. This carbon is going to be more electronegative, and there should be positive charge generates on the nitrogen over here. So that positive charge should be satisfied by this electrocloud. So the positive charge now shifted on nitrogen itself, and here this pi electrocloud is going to shifted over here, and a negative charge generates on this carbon. To satisfy that negative charge, again the electron will shifted over there, so positive charge generates and the negative charge shifted on this hetero element. And then after this, so 1, 2, 3, 4 and 5 resonating structure is going to be obtained, which indicates the aromatic nature of this heterocyclic 1,3 azole. Here X represent nitrogen, oxygen or sulfur, not for halogen. The proton chemical shift that is in delta ppm is given for this compound. Imidazole, oxazole and thiazole. When here nitrogen is there and oxygen is there, two nitrogen is there, sorry, then it is imidazole. One nitrogen, one oxygen, oxazole. One nitrogen, one sulfur, that is thiazole. And each are having second carbon containing a proton, third carbon, fourth carbon containing a proton, and fifth carbon containing a proton. So H2, that is second number carbon contain a proton, H4, that is fourth number carbon contain a proton, and H5, that is 5 number carbon contain a proton. Imidazole contain 7.86, 7.25 and 7.25. These are two equivalent proton, and this is little different proton that you can see in the same kind of behavior in this one, and there is little difference in the thiazole for the delta ppm value of the thiazole proton in the ring. Now imidazole and benzimidazole, that means this is a 1,3 azole, this is fused ring structure. Imidazole and iminozoline is a azapyrrole. the nitrogen atom being separated by one carbon atom, that is 1,3-azole. This compound was earlier also called as glyoxylene, as it was prepared in 1858 from glyoxal and ammonia. The benzo derivative is referred as benzimidazole, that is a fused structure which we are going to discuss later on. The imino nitrogen is assigned position 1 and the tertiary nitrogen atom position 3. So this one is going to given a priority compared to the tertiary nitrogen. The imidazole nucleus is found in a number of naturally occurring compounds like histamine, histidine, pilocarpine, and allantoin. The benzimidazole nucleus appears in vitamin B12. So here are the two structure, imidazole and benzimidazole, fused ring structure. This one is an imino nitrogen and this one is a tertiary nitrogen. So this one is given priority, 1 number, 2 number and 3 number. We cannot give numbering from this side. Similarly for here, for this benzene fused structure also, the second nitrogen should come in a minimum numbering. Now tautomerism in imidazole. Imidazole with a ring hydrogen or a hydrogen attached with the nitrogen are subject to tautomerism, which becomes evident in unsymmetrical substituted compounds such as the methyl imidazole. The specific feature of imidazole chemistry means that to write simply for methyl imidazole would be misleading. For this molecule is in a tautomeric equilibrium with 5-methyl imidazole as well and quite inseparable from each other. And instead of only 4, it is written as 4,5-methyl imidazole. So all such tautomeric pairs are inseparable and convention used to cover the phenomena is to write 4,5 instead of only 4 or only 5 because of these two tautomeric effect of the compound. Will using the nomenclature in this way for a substituted imidazole 4,5-methyl imidazole. In the same pair, one tautomer predominates. For example, 4,5-nitroimidazole favors the 4-nitro tautomer by 400:1. So here 4,5-methyl imidazole, which is in a tautomeric form, and these are the resulting structure where either you can indicate it on the 4 or 5. So 4, 5, 2 position would be there. So these two are equivalent and it is inseparable. They are tautomeric form of each other. Now dihydroimidazoles are referred to as imidazoline and 3 of them are possible. These are 2-imidazoline, 3-imidazoline and 4-imidazoline. Out of these, 2-imidazoline are most common. These are monoacidic bases and can form monohydrogen halide salts. Here you can see this is 2-imidazoline, this is 3-imidazoline and this is 4-imidazoline. Physical and spectroscopic property. Imidazole is colorless liquid having boiling point 256 degrees centigrade as compared to pyrazole, the boiling point 187 degree. So you can see imidazole is having higher boiling point. We will learn the reason behind this, and is a high boiling point than all the other 5-membered heterocyclic compound, and the reason for that we're going to study. In a marked contrast to imidazole, the boiling point of 198 degrees centigrade for 1-methyl imidazole is comparatively low. This data demonstrate that the hydrogen bonding exists in imidazole. This is the reason behind these two difference in the boiling point of these two 1,3-azole. Hydrogen bonding exists in imidazole ring to the type or as shown below by consisting of up to 20 molecules. 20 molecule chain, long chain is there, and as a result of that, the boiling point is going to be all time higher in imidazole compared to rest of the heterocyclic compound. Imidazole is more basic. The pK value would be 7.2 compared to pyrazole and pyridine. Even pyridine have pK 5.2, and this is even higher than that. That means the basic nature of imidazole is highest as well. It shows amphoteric properties and behave as an acidic because it contains pyrrole type of imino-nitrogen. So that nitrogen has one proton as well, and that proton make it acidic in nature, and this is more basic as well by the tertiary nitrogen. So it is amphoteric in property and forms metallic salt with either sodium amine NaNH2 and with Grignard reagent RMGX, which are extensively hydrolyzed by water. So the introduction of alkyl group into the ring increases the basicity to methyl imidazole, where having pK value 7.86, which is even greater than the imidazole, substituted to methyl imidazole as having higher basic nature, and 4,5 methyl imidazole is even having higher basic nature compared to imidazole. So these two is going to have higher basic nature. The substituted imidazole is going to have higher basic nature, so we suppress the acidic nature of imidazole as well. Imidazole is an aromatic compound, possesses a resonance energy of 14.2 kilocalorie per mole, which is almost half the value of pyrazole. The dipole moment of imidazole has been measured in several solvents. In dioxane, the value would be 4.8 dBi, indicates a considerable polarization in the imidazole ring. Now, synthetic methods. The Rizowski synthesis. In Rizowski synthesis, we have these two dione treating with ammonia in presence of benzaldehyde will going to get the substituted imidazole. A dicarbonyl compound, this is dicarbonyl compound such as glycol, alpha ketoaldehyde or alpha diketone with an aldehyde, this is benzaldehyde in presence of ammonia, benzyl, or for instance with benzaldehyde and two molecules of ammonia react to gives 2,4,5 diphenyl imidazole. Formaldehyde often prove a convenient substituent for ammonia. Dehydration of imidazole. Here you can see this is diamino compound, and that diamino compound treated with this tertiary amine will going to get the cyclization and will get this substituted imidazole, which treated with barium manganate will going to get substituted imidazole. Imidazole have been prepared by dehydrogenation of imidazoline in presence of sulfur. However, a mild reagent, barium manganate, has been recently reported by Knapp and co-workers. So this Knapp synthesis as well. Imidazoline thus obtained from alkyl nitriles and 1,2-ethane diamine on reaction with BaMNO4, that is barium manganate, yields two substituted imidazole, and it has been obtained as one of the byproduct in other reactions. Now from alpha haloketone we can synthesize imidazole as well. Alpha haloketone treated with this amine compound and we're going to get the substituted imidazole. This reaction involves the interaction between an imidine and alpha haloketone. Imidine and alpha haloketone will going to give you substituted imidazole. This method has been applied successfully for the synthesis of 2,2 or either 2,5 diphenyl imidazoles. Phenyl acyl bromide and benzimidine According to this method, for 2,4 diphenyl imidazole. Similarly, imidine reacts with acyleons or alpha haloketones to yield imidazoles. This is the reaction for that. Now, preparation of benzimidazole, the fused ring structure of 1,3-azole. Benzimidazole is more important than imidazole as the former occurs in vitamin B12 and has been prepared by a number of methods. 1,2-diaminobenzene condense with a carboxylic acid on heating in a acidic medium to give benzimidazole. Here is the synthesis of benzimidazole, where you can see this diamino derivative treated with this carboxylic group at 100 degrees centigrade temperature. Condensation will going to give you a substituted benzimidazole. Chemical reaction of the benzimidazole. Reaction with acid. Imidazole is a monoacidic base and forms crystalline salts with acid. It also possesses weakly acidic property, as you know. It is amphoteric in nature, so pseudoacidic is there as well, and it is even more acidic than pyrrole and thus forms salt of following type of Grignard reagents or metal ions. So you can see that imidazole treating with this proton will going to gives us these two resonating structure that treated with magnesium in zero oxidation state with halide in dry ether will going to give us imidazole magnesium chloride, that is a kind of Grignard reagent. Now electrophilic substitution reaction, carbon 2, this carbon where we are going to use the electrophiles will going to gives us this three resonating structure. For carbon 4, that means this position, it will going to apply electrophilic reagent, will going to get only two resonating structure. For carbon 5, at this position, when we are going to apply the electrophilic electrophile, it's going to give us three resonating structure. So carbon 2 and 5 are the most specific site for entering the electrophiles into this 1,3-azole. The contribution of a charge structure of imidazole are more important than those of benzene. For this reaction, imidazole possesses increased reactivity towards the electrophilic attack. It is more susceptible to electrophilic attack than pyrazole or thiazole, and even more so than even furan and thiophin as well. Through the resonance structure of an intermediate ion, it is evident that the attack takes place at the 4 or 5 position, because this is going to give you tautomeric effect in imidazole. It may be noticed that the attack at carbon 2 involves a canonical forms with a highly favored position of nitrogen at position 3. Halogenation of imidazole, that is electrophilic attack. Halogenation of imidazole is very complex and varies considerably depending on the substrate, reagent and the reaction conditions. Direct chlorination gives undefined product. Bromination in presence of chloroform yields 2,4,5 tribromo derivative. Here is the reaction for 2,3,4 tribromo derivative. 2,4,5 tribromo 1-methyl imidazole. Iodination of imidazole. Iodination of imidazole take place in alkaline condition to give 2,4,5 triiodoimidazole. That 3 substituted imidazole fails to iodinate leads support to the theory that it is the imidazole anion which reacts. The anion is actually 10 times more reactive compared to neutral molecule. So here you can see the position second is the most favorable and fourth position would be there as well. So here you can see the fourth or 5 tautomeric effect would be there. So we're going to get the fourth or 5 membered iodoimidazole. Iodination of 2,4,5 triiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiodoteiod imidazole shows a large kinetic isotope effect, that is Kh by Kd, that is almost 4.5, which indicates that loss of a proton from carbon 4 is rate controlling in monoiodination reaction, and that is why for substituent we will going to obtain in large amount. Bromination of imidazole. Bromoimidazole can be converted into chlorimidazole by refluxing with HCl. Direct chlorination is difficult, but this way you can get the chlorine element on imidazole. Both nitration, fuming HNO3 with H2SO4, and sulfonation, oleum with 100 degree centigrade, afford the 4,5 imidazole derivative due to tautomerism. If these positions are occupied, then imidazole fails to react in nitration and sulfonation. That is a limitation of this electrophilic substitution reaction. Diazo coupling, on the other hand, take place at position 2. If this position is occupied, then it occurs at 4,5 position. Mercuriation take place at 4,5 position, and in imidazole the electrophilic substitution take place at 4,5 position, but the reverse is true for the deuteriation. Deuteriation, sorry. Reaction with oxidizing and reducing agent. Imidazole itself is stable to auto-oxidation and to action of chromic acid, but it is attacked by KMNO4. Oxygen in the presence of a sensitizer, single oxygen react to give an imidazolene derivative. Imidazolium dichromate, a mild oxidizing agent, has been employed for the oxidation of allylic and benzylic alcohol to the corresponding carbonyl compound. Benzothiazole. This is 1,3 position of the fused ring structure of benzothiazole. Benzothiazole is an aromatic heterocyclic compound with a chemical formula C7H5NS. It is colorless, slightly viscous liquid. Although the parent compound benzothiazole is not widely used, many of its derivatives are found in a commercial product in nature. Derivative of benzothiazole is the light emitting compound of luciferin found in fireflies. This is the structure. Benzothiazole consists of a 5-membered and 1,3-thiazole ring fused to a benzene ring. The 9 atoms of the bicyclic and the attached substituents are coplanar. So here is going to be the coplanarity of the compound of benzofused structure. Properties: the chemical formula is C7H5NS, molecular mass that is 135 gram per mole, density 1.238 gram per ml, melting point 2 degrees centigrade. Spectral data is available in UV, IR and NMR. Preparation: benzothiazoles are prepared by treatment of 2-mercaptolene with acid chloride. 2-mercaptolene with acid chloride will going to give you the substituted product. The heterocyclic scaffold is readily substituted at the unique methine center in the thiazole ring. It is thermally stable, electron withdrawing moiety with numerous applications in dyes industry such as thioflavine. Some drug containing this group, example being riluzole and pamipexole. The heterocycle is found in nature accelerator for the vulcanization of rubber and are based in 2-mercaptobenzothiazole. This ring is a potential component in non-linear optics, that is NLO. Well, this is enough from my side. Thank you very much for paying attention to this video lecture. Hope you have taken interest in heterocyclic chemistry is a research topic, and therefore keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you.